All right, well, good afternoon, everybody. Thanks for joining us today for our third episode of For Our River webinar series. My name is Emily Floor, and I'm the Executive Director for St. Mary's Riverkeeper. Today's webinar is an opportunity for everyone to learn more about groundwater, specifically the Floridan aquifer, and the impacts water withdrawal will have on surface water flow and drinking water for the Southeast. This episode will hopefully address and answer some of the complex issues and questions you may have about the proposed mining project impact on the water levels of the St. Mary's River and the Okefenokee Swamp. Each of these episodes focus on a specific topic with a different subject matter expert and allow time for discussion from our participants to help understand each topic better. You can find last week's webinar about wetlands and carbon capturing, that recording on our website under advocacy webinars. Today, we are joined by Dr. Jeremy Stalker from the Marine Science Research Institute at Jacksonville University, and we will dig, pun intended, into the role of human and industry consumption has on groundwater levels. But before we get to that, we're going to discuss St. Mary's Riverkeeper's work to protect the St. Mary's River, our efforts to monitor and educate the public about our river, and ways you can engage today. We will then hear from our guest expert and end with Q&A from our viewers. So to begin, let's talk about what St. Mary's Riverkeeper is and what we do. Founded in 2016, St. Mary's Riverkeeper is an independent voice for the St. Mary's River, dedicated to improving water quality in areas that are designated as swimmable or fishable, ensuring the river thrives for future generations with our work in resiliency projects and community partnerships, promote low-impact development in a fast-growing area, finding solutions for water-related issues in the watershed, and advocating against industrial threats in our underserved communities. As a trusted voice for the St. Mary's River, Riverkeeper fulfills its mission by investigating pollution problems, seeking solutions to protect the St. Mary's River, ensuring environmental regulations are implemented and enforced, advocating for the protection of our river, and participating in decision-making processes to represent the interest of our river, our members, and the public, educating the public about the St. Mary's River and issues impacting its health, providing frequent opportunities for people to experience the river and serve it through river cleanups, boat rides, and field trips, and engaging with citizens to effectively resolve problems impacting the river and their neighborhoods and communities. As a border river, the St. Mary's River watershed is comprised of 4 counties, 2 in Georgia and 2 in Florida, with roughly 60,000 residents who depend on the health of the river for tourism, recreation, commercial fishing, and drinking water. Arising from the Okefenokee Swamp, the St. Mary's River flows 130 miles to the Atlantic Ocean at Cumberland Island National Seashore. The watershed has over 3,000 miles of streams and tributaries, is comprised of 40% wetlands, and is home to many endangered and threatened species such as the Atlantic and short-nosed sturgeon. The shape of the St. Mary's River is defined by the natural break and trail ridge. The Okefenokee Swamp and the upper St. Mary's section of the St. Mary's River runs along the western side of Trail Ridge. The river then turns eastward for about 15 miles, running through the only gap in the ridge, and then it heads north for about 30 miles along the eastern side of the ridge. At Folkston and Hilliard, it starts heading east out into the Atlantic Ocean. The southeastern corner, about 20% of the swamp, feeds the St. Mary's River, which results in the upper river having zero flow at times and flooding at others. From swamp to sea, the St. Mary's River is pristine. The land along the St. Mary's is almost entirely privately owned by timber plantations and private citizens. In 2022, Georgia DNR declared 2 segments of the St. Mary's River safe for recreational use: Deep Creek to Boone Creek, and Prospect Landing to Little St. Mary's. This upgrade means that the EPD, which is under DNR, is committed to protecting these segments for recreation with higher levels of acceptable water quality. Some of our efforts to make sure our river is protected is our extensive water quality testing program led by our citizen scientists trained in a Georgia Adopt a Streams protocol. Our river cleanups, we'll talk about one that's coming up in April near the end. Our experiential learning opportunities, which we do paddle trips, bike rides, and boat rides. Our river enhancement projects, such as our living shorelines in downtown Fernandina Beach, and then our advocacy and engagement opportunities. Some of our upcoming events that we have, of course, is the Mining Public Comment, which closes March 20th at 4:30 p.m. We have our river cleanup, this is watershed wide, Last year, we had 350 volunteers pull 8 tons of trash out of the St. Mary's River and its shorelines. Our boat tour is fortunately, but also unfortunately, sold out for this Saturday. But please become a member to start receiving our newsletters to see when our next one will be scheduled. And then our next Lunch and Learn, which is the final one of this series, is next Thursday, March 16th, with James Coughlin from Camden County Development Authority and Angela Wigger from St. Mary's Convention and Visitors Bureau to discuss ecotourism in a gateway community. So I'm going to talk a little bit about some of the groundwater impacts from the mining permits, and just to give you a little bit of background before we start with Dr. Stalker today. So Trail Ridge is a former sand beachfront that is 1 mile wide and around 100 miles long. It's a topographic ridge that separates the Okefenokee Basin and swamp from the coastal plain of Georgia. It runs from Georgia and into Florida and is rich in heavy minerals such as titanium-bearing ores such as ilmenite and rutile, which is processed to make titanium dioxide, a key component of some of the widest, brightest, and most efficient applications, such as paint, a durable automotive and aerospace coating. It's also in your sunscreen. It's also in Skittles, apparently. So the mining plan sheet, or the Twin Pines mine, proposes an experimental techniques for mining heavy metals during the 4 years of this proposed project. Since there are no jurisdictional wetlands on the mine site, the mining company does not have to work around any wetlands and can destroy all wetlands and trees on the 582-acre site. The pit they will excavate will be a max of 500 feet long, 100 feet wide, and 50 feet deep, moving at a speed of 100 feet per day or 10 to 15 acres per month. The excavated materials will be moved to on-site processing facilities using a mobile conveyor where heavy minerals will be removed from the sand. About 98% of the mined sand will then be returned as spoils to the inactive portion of the mine pit. The topography of the reclaimed mine spoils, they say, will be returned as close to pre-mining elevations as possible. The post-project wetland area will be roughly equivalent to the pre-project wetland area, and upland areas will be reconstructed with native longleaf pine. The proposed mining activities, this is only for 4 years. They're saying the total amount of time that they want to mine is 11 years. So they have more property just north of this. This is a light detection and ranging map, or a LIDAR map. And it shows the proposed mine here in this polygon shape with the diagonal lines through it. Sits on the crest of the ridge, so there is a hydrologic divide running through the mine. Ironically, both sides of the ridge flow to the St. Mary's River. The west side flows to River Styx, which flows to the swamp and then to the St. Mary's, and then Boone Creek off to the east, which is a tributary of the St. Mary's River. This is from one of their permits. This shows the water table of Trail Ridge, and you can see it's shallow and mimics the topography of the ground surface. Precipitation that is not evaporated or transpired to the atmosphere infiltrates to recharge the surficial aquifer. Along the western margin of the proposed mine area, groundwater flow provides water to the Okefenokee Swamp and related wetlands. On the eastern side, groundwater provides flows to streams that then go out to the St. Mary's River. The surficial aquifer underlain by the sediments of the Hawthorne group, which is down here at the bottom. And that's approximately 350 feet thick under Trail Ridge and has low permeability, is made up of calcium-based clays, which isolates the surficial aquifer from the Floridan aquifer. This is an image taken from Dr. Rhett Jackson. The mining company is asking to remove 1.44 million gallons of water a day from the Floridan aquifer from 2 wells that reach down into the Floridan aquifer. However, as we all know, when you dig a hole around here, it immediately fills up with water. So to be able to run their experimental techniques of drag lining, the company will need to dewater the pit continuously. They estimate removing 1.1 million gallons of water a day just from the pit. EPD, in their December 2022 memo, stated that they have modeled the impact of the Floridan aquifer pumping loss on the swamp and concluded that the water level in the swamp will have an impact of roughly 5 millimeters at the worst. and dewatering from the mining pit may have a higher level of connection with the superficial aquifer or the swamp than the Floridan aquifer withdrawal. So how are we all connected by groundwater, and what happens when we overpump from one source? So to answer that question, we have Dr. Jeremy Stalker here. He is an associate professor of marine science at Jacksonville University from the Marine Science Research Institute. He earned a BS in geological science at Michigan State University, an MS at geophysics at the University of Montana, and a PhD at Florida International University in geochemistry. He has taken a path of academics and professional work in his career. Besides his academic degrees, he has worked as a hydrologist for the United States Geological Survey, as a geophysical consultant in southeastern Alaska, and as a private hydrologic consultant. So I'm going to stop sharing my screen and turn it over to Dr. Jeremy Stalker. Thank you for joining us today.
Thank you for having me. Okay, so now my turn to share my screen.
And as he's figuring that out, if you have questions during the presentation, please put them in the Q&A. I will answer the ones I can and leave the rest for Dr. Stalker at the end.
You all see the alligator propped up on a log?
Yes.
Okay, perfect. All right, well, that's a great primer. So I'm going to talk a lot about some more sort of generalized ideas of hydrology and how this works. We'll talk through a superficial aquifer system. We'll talk through a confining layer and what the Floridan aquifer looks like, and we'll look at some of the areal extent. But I just want to go through sort of a little primer on hydrology and sort of how these things are connected. So bear with me. Hopefully I'm not insulting anyone's intelligence as we walk through this, but a little reminder here and there is never bad. All right, so just let's talk about some things. So what's groundwater? How do we define it? Really, it's anything that's trapped under the sediments or the rock under the surface, right? So we consider surface water anything above, groundwater is anything below. There's this zone called the vadose zone that sits between the two, which is a partially watered zone, where water flows from the surface down to the water table. We'll talk about that sort of stuff when we look at some diagrams. So most of the fresh water we use in the United States, at least a lot of it is from groundwater sources. Here in this part of the United States in the Southeast, we're lucky to have the Floridan aquifer. It's actually one of the largest and most productive aquifers in the world. Those stats are a little fuzzy, but it is in the top 3 in terms of the amount of water it produces, the number of people that actually get water from it. I remind my students every once in a while, we're quite lucky that we can draw water from the Floridan because we're drinking and using first run water. In other words, water that's come directly out of the aquifer system. There's some places like Los Angeles that have water sources that are heavily reuse. So you get a lot of water that's been processed as opposed to coming directly from the aquifer. All right, so we're going to talk about some flow paths, and groundwater is quite complex, especially in places like Florida. Sometimes it can be very young. In other words, the rainfall from yesterday has infiltrated into the aquifer system. So we're talking about water that's very young. And sometimes we can have groundwaters that are quite old. So in the oldest cases, there are aquifers, say in Jordan, some in Egypt that are hundreds of thousands of years old. They're from the old ice ages. Right now here in Florida, the oldest stuff we see coming out of the Floridan aquifer can be as much as 100 years old, but it's generally younger than that. We'll talk about the layers of the Floridan and how it's not quite all uniform. All right, just another sort of very quick primer on water. The hydrologic cycle sort of links everything, and it's really neat to think about how this works. Almost all of the movement of water, and for that matter, air on our planet, is driven by heating from the sun. Right, so very warm at the equator, very cool at the poles. That drives our bigger currents in the oceans. It drives our air masses, but it also drives water moving through the planet. So everything evaporates, it goes up, it trans-evaporates from plants, it gets put into the atmosphere. Its residence time in the atmosphere is quite short, so we don't have a whole lot of water in the atmosphere, but we have enough to cause rain and snow. Right, that comes back down, and it takes different pathways. Some gets taken up by the plants. Some of it does this and it goes down into the infiltration through the soil, into the aquifers, and some will run off in rivers. And it's even more complex than that, especially when we start talking about rivers. We'll talk about lakes and rivers and wetlands. But just remember that all of this water is moving continuously through the cycle. It spends different amounts of time in each of these reservoirs. As it moves from one to another, it carries all sorts of stuff with it, including lots of elemental material that we need for life on Earth, but also distributes it to the oceans and from the oceans back onto the landmass. All right, and this last piece that I always like to point out, especially here, all of these are connected, right? So we're going to talk about different layers of aquifers today. I'll emphasize in a few places that these are all related, right? They're all connected to each other. And indeed, the aquifer systems here are intimately connected with the surface water areas. So we'll talk about how it sort of moves in between one and another. All right, so just a few other things we should think about. The ability for sediments and rocks to hold water are based on a couple of concepts. The first one's porosity, right? So different mediums, in other words, different kinds of earth materials have different porosities. So these are the void spaces in between the grains. So if you can imagine, like, you have a cup of sand, right? And you pour water into it, the water flows in between the grains of quartz or whatever happens to be making up the sand and fills those porous voids in between. So when we're talking about an aquifer system, we're talking about the water that's sitting in between these voids. So the more porous a rock is, or a sediment is, the more water it can contain. Yeah, so we'll get to that more in a moment. All right, just sort of some ideas about porosities and rock types. Here are just some random sort of common aquifer materials, soil materials. So something like sand. So if you just have a sandbox or a beach, it has about 20% void volume. In other words, about 20% of that sediment is made up of voids. So that's 20% that's potentially fillable with water, if you will. Sand and gravel, if you start throwing some pebbles in there, it increases the porosity by about 15%. They're bigger voids, right? So you can fit a little bit more water in. Now, a couple that we're interested, especially around here. So we'll talk about sand being, that's making up a lot of our superficial aquifer system. The clays we talk about, clays are interesting because the grains are very, very small. Clay and clay-like substances have a high porosity. In other words, there's a lot of area between the grains to fit water. But we'll talk about why clay isn't a great aquifer because it has low permeability. So there's a bit of a difference between those two concepts. We'll talk about permeability next. But just keep in mind that clay actually has a lot of porosity. Now, limestone itself, which is the building block of most of our big aquifer systems down here, limestone is a crystalline rock, and it's actually quite poor in porosity if it's just normal everyday limestone. Right? It's actually quite crystalline. If we change that and we make it karst limestone, you increase the porosity intensely, right? So it can go up to 50 to almost 80% in terms of porosity. The limestones around Northeast Florida, and most limestones actually, are karstic. We'll talk about what makes karst. But just keep in mind that the reason the Floridan aquifer is such an amazingly productive and good aquifer is because it's karstic. So it has this really big porosity. All right, so our next concept is permeability, right? So permeability is the connectedness of these pores, right? So you can have lots of water in clay, but the pores are very poorly connected. In other words, it's really hard to draw water out of it simply because you drill a well into it, you only penetrate a certain number of these voids, and once you've drained those, it's very hard for water to move through the clay to get to the pumping well. So just on a side, if you guys know about fracking, which is something that happens out west quite often, fracking occurs in these shales and clays where there's a lot of porosity, so there tends to be a lot of natural gas and oil trapped in there, but it's hard to pump out. So they frack the rock to break it apart, and that fracking increases the permeability, right? So it fractures the rock up so it connects pores. Now, there are lots of rocks that have natural permeability or naturally high permeability. In the case of limestone, that's what's happening here. Our sands and sort of sediments that make up the superficial aquifer. So you'll notice in this sort of lower graph, we've got water that can easily move from one pore to the next. The more permeable a rock is, it means the better you can pump water out of it. But we'll talk about what that also means in terms of pumping and cones of depression. But keep in mind that you have to have porosity and permeability to make a good aquifer. You can't just have one or the other. All right, so aquifers sort of come in different flavors. And there are all sorts of different substances that make up aquifers, but we sort of bin them into two parts. So one is called an unconfined aquifer, and then the other is a confined aquifer. So we're going to sort of talk about the two differences between these. So a couple concepts to know. The USGS and the federal government, the state of Florida, the state of Georgia, all sort of identify or define an aquifer as a body of sediment or rock that can produce commercial amounts of water. Now, that's a very vague and fuzzy term. What does commercial mean? Ideally, there aren't even like millions of gallons per day limits to what makes an aquifer or not. If you drill a well in your backyard and you can pull enough water out of that, whatever you've drilled into to meet your needs, technically you've drilled into an aquifer. Right now, on a commercial level, we're talking about supplying something like the city of Orlando or Atlanta, right? So you need pumping from an aquifer that's big enough to supply a very large demand. Okay, so those sort of technical and even legal terms aside, let's talk about our two kinds of aquifers. All right, so an unconfined aquifer is also referred to as a water table aquifer. The water table is the line of 100% saturation in the earth, right? So if you drill a well down, you're going to drill through dry, ostensibly dry sediments. You'll start to drill through what we call sort of partially wetted or moist sediments. And then finally, you'll hit the water. So when you drill a hole, the water rising in the well, if you're in a superficial aquifer system, that's the water table. And something to remember is in most landscapes, rivers, lakes, and swamps are generally the surface expression of the water table. So when you see a borrow pit in, say, a housing development, and you see the water level in that housing development pond, that's mirroring the water table sitting beneath the land around it. In other words, what you're doing is you're sort of cutting a window into that superficial aquifer. All right, so these aquifers are open to the atmosphere and the surface, which means anything you put on the surface can make it into the aquifer system itself. Rainfall will replenish or refill the aquifer, and any withdrawals or even evaporation on some level can remove water from the aquifer. We'll talk about groundwater flow in a minute, but I just want you to keep this idea that these superficial aquifer systems fluctuate, right? So they go up and down depending on our climatic conditions. The other one, so the much more sort of, I don't know, weirder, more complex systems are these things we call confined aquifers. So confined aquifers have some sort of layer that separates them from the surface, right? And we'll call these things all sorts of names. They're aquicludes or aquitards. So they are some sort of substance that does not allow immediate flow. In other words, they have very low permeability. So if you have a low permeable layer, the aquifer below it is considered to be confined. In other words, it's under pressure. And the behavior of confined aquifers is very different than the way water table or superficial aquifers work, in that the recharge areas for these confined aquifers are wherever that confined aquifer meets the surface, right? So where it crops out on the surface is going to be its recharge zone. And that water will proceed into the aquifer and increase in pressure. So the deeper the confined aquifer is, the higher the pressure is on the water. And when you puncture a confined aquifer, the water in the confined aquifer will rise in that well up to the point of essentially wherever it crops out. So let's say your aquifer is 200 feet below your surface and the recharge area is 100 feet higher than where you're standing. It means that water is going to rise up that 200 feet to the level of about 100 feet above your surface. So what that means is a lot of these confined aquifers produce what we call artesian wells, or wells that flow without pumping. They used to be more common, but as we've drawn more water out of these sort of aquifers, they're less common. But there are even old stories down in Miami about the Floridan aquifer actually upwelling in Biscayne Bay, and you had freshwater boils that came up to the surface in the seawater. So just give you an idea that these artesian wells are puncturing a pressurized system. So our Floridan aquifer is confined. We'll talk about the Hawthorne group, but the Hawthorne group is what confines the upper Floridan. And that Floridan aquifer is otherwise, it's under pressure. In other words, if we puncture it, the water will rise in the well. We're going to talk about how this isn't quite that simple either, right? Because nothing ever is in nature. All right, so unconfined aquifers, and when we're talking about this, what I want you to be picturing is this surficial aquifer system. So this is what's sitting on the surface. It's what most of us are standing on at any given time. In this area, we're standing on the surficial aquifer system. Our surficial aquifer system, we'll look at some maps soon that show us we're talking about mostly unconsolidated sands, and clays, basically from lots of beach sand from the Mississippi, from the Swanee, some from our older rivers flowing into a different landscape back in the Miocene. But these water tables are up and down depending on the amount of rain. So you can imagine during our wet season, the water table rises. During the dry season, it drops. Most of the aquifers we use in the US are actually surficial aquifer systems. They're good in that they recharge with rain. It's bad in that they're very, very susceptible to contamination, right? Because it's quite easy to pour stuff on the surface that'll make it down into the water table. So we're going to talk about this more in a minute, but we have two different examples here. So on the left, what you're seeing is a high water table, right? So our river level is high. We have wetlands that are filled with the water table on our sort of right-hand side of the river. And we have rainfall coming down, so we're recharging this system. During drier seasons, we have what becomes a losing system. So the river, wherever the water is coming from the river, starts actually flowing out of the river into the water system. So we're losing water out of the river into the aquifer. You notice our wetlands have dried up, right? So we have this sort of seasonal fluctuation that has to do with this change in the water levels in our wells and the surface of the land. If we look at it in cross section, so if I slice into that sort of image I showed you in the last slide, and we look at it in 2 dimensions, this is sort of the makeup of how water tables work, right? So water tables generally follow, I think Emily mentioned this, they follow the contours of the land. So the land's higher, the water table is going to be higher. So if you're in this sort of central zone here, right, and you're up on this hill where it says water table, the depth to the water table is going to be shallower than if you sort of move downstream, right? So water is going to actually build up in this hill and it'll flow from this hill. So this high pressure, if you will, where it's higher and closer to the land, it'll flow to these low areas like the stream and the lake, right? So what we have is this general flow pattern of water flowing from our higher regions down to our lower regions. And in that image you were seeing earlier of like where the mine site was, right? They're slapping on top of one of these ridge crests. You can start thinking about, how that might affect the hydrology, right? So in this case, we have water that collects here at this ridge. Half of the water is going to flow to the stream, half the water is going to flow to this lake. And given the fluctuation in the water table, the stream and the lake will get differing amounts of feed from that water table. Just some ideas of what these look like. So typically places like out west where I used to live, it's a sand and gravel aquifer. So literally what the aquifer looks like is this picture here. Lots of pebbles, lots of grains, makes a very productive surficial aquifer system. On a very different note, right, this one down here, this is the karstic limestone of the Floridan. So it looks like Swiss cheese, right? It looks like it's a very different kind of rock. So at one point, if you can imagine, that limestone down there was solid, right? So it was a solid chunk of rock. It would look more like a piece of concrete. But things change that limestone, their chemical changes that dissolve out cavities and create this very, very porous and very, very permeable rock. So this kind of karstic rock only makes up a few places. You can sort of see in the brown in that map of the US where we have these sort of carbonate aquifer systems. They're not common and they're exceptionally productive. So these are excellent aquifers. But there's also, we're going to talk about a lot of potential for abuse and even contamination of these systems. All right, so sort of some mechanics of our confined aquifer system. On our image here, you sort of have this black line. So the black line is measuring up to where that confined system is connected to the atmosphere. So the sort of strip of land up here where it's raining, that's what we call the recharge zone. So that's where we're going to recharge this aquifer. So you can imagine this is the Floridan aquifer. We're going to look at some maps in a minute. The Floridan aquifer is quite extensive. In other words, it covers an enormous amount of the southeastern United States. But the recharge zone for it actually only happens in a few places. In other words, we only refill that Floridan aquifer in a few places. And if you puncture that aquifer, right, as you sort of drill these wells down the hill, this first well, it's kind of close to the source. Water will rise up to that original level. So if you look where the level in the black line is the recharge zone, it'll literally flow up to that level. Down here further in the valley, when you've drilled your well, it's going to still flow all the way up to that line, right, that potentiometric surface. But that means it's going to be flowing above the land. And on the right here is an example of an artesian well, an extremely high pressure artesian well. I think this is from Texas, that also has oil in it. So you get sort of both. But in this case, you'll see that water can actually flow. So often with artesian wells, you don't even need a pump. It just simply flows. Okay, so sort of two concepts, inflow with recharge and outflow with discharge. So recharge occurs anywhere that infiltration of rainwater streams will intersect the aquifer. So in the case of a superficial aquifer, that's the entire water table, right? So anywhere that water can infiltrate through the soils or the sand that makes up the superficial aquifer, it's going to make its way into the aquifer system. For these confined aquifer systems, the inflow recharge areas are much more minute, right? So it's not as widespread, it has much smaller footprint. Now, reversely, the outflow, or where the groundwater ends up, is called the discharge zones. So discharge can happen in river systems. So rivers can be fed by groundwater systems. Wetlands can be fed by groundwater systems, and they commonly are. Or these can flow out to things like springs. We'll look at springs in a moment. Springs are simply the discharge areas of the Floridan aquifer. Okay, so a losing stream, we talked a little about this. This is common in the Western United States. The reason I bring this up is because if you start intensely pumping an area, you can force changes in a river to go from a gaining river to a losing river. So a losing stream, in other words, water is flowing out of that losing stream into the aquifer that surrounds it. The gaining stream, on the other hand, we have discharge, or we have water coming from the groundwater system into the stream. This is more common, especially out east. In mountainous areas, you often have gaining streams where water flows out of the surrounding aquifer into the river. Most tropical river systems, if you think of things like the Amazon, right? So the Amazon is actually also a groundwater fed river in most places. The St. Johns River down here in Jacksonville is almost an entirely spring-fed river. So there are a number of springs that feed into the St. Johns from the aquifer system. So it's actually quite intensely related to what's happening in the aquifer that surrounds it. Okay, so one way we measure these sort of things is by looking at hydrographs. So hydrographs are a plot of the discharge. So you measure how much water is flowing through a river or a stream. You could even do this in wetlands. And you look at the amount of water coming through time, right? So in this case, we have two different kinds of rivers. The Sturgeon River in Michigan is a gaining stream. The Forest River in North Dakota is a losing stream. The differences are, so the Sturgeon River, even at the times of relatively small rainfall in January through December, there's still a significant amount of discharge in the river, which means the banks of the river and beneath the river have water flowing through them into the river, and it's giving you discharge in that system. So the river will not run dry. In North Dakota, you can see the dry season in December to January. The flow in the river is much closer to zero because there isn't any runoff into the river. And in some cases, these rivers can actually go to zero discharge, which means actually any water in the river is probably flowing into the aquifer system. And again, the reason I bring this up, most of our rivers here in the Southeast are gaining rivers. But if you pump intensely near a river system, you can drive it from one condition to another, depending on how much water you remove from the aquifer. All right, so let's sort of talk about our local area. So I'm going to show you some images, a lot of these from the USGS, NOAA, things like that. So I'm going to give you just some background into what the Floridan aquifer system and our aquifers look like in this area. All right, so what we're looking at here, this is the Floridan, right? So this is the extent. That black line is essentially the end of the up dip of the Floridan aquifer. So kind of think of this like one of those cartoons where the up dip, in other words, the rock is shallower in the north and it gets deeper as you go south. So the Floridan aquifer will actually be at the surface in places in Georgia and sort of western Florida. Whereas if you get onto Miami, there's still the Floridan aquifer down there. It's just very, very deep, right? It's under a lot more sediment. So the Floridan aquifer, you can imagine, is sort of like this ramp going from north to south and going from up to down from north to south. So think of this sort of inclined rock body. Okay, so the Floridan aquifer system itself is a number of layers. We differentiate it starting at the Hawthorne Formation. So the Hawthorne Formation is what we call an aquitard. It is the confining layer that sits above the Floridan aquifer. And we'll look at it, it's variably thick depending on where you are. Some places it's very thin, so sort of up near Georgia, and some places in eastern Florida, the Hawthorne group is actually quite thin. And it's broken in some places, so there are holes in it, if you will. In some places down near Tampa, and as you get further south towards Miami, it gets much thicker. So the Hawthorne group is this aquitard, and we'll talk about what sort of it's made out of in a moment. But it keeps the confined layers below it. So there's actually an upper Floridan and a lower Floridan aquifer. They are separated by another exclusion layer or an aquitard between those two. So there's kind of like it's kind of like one of those yummy cakes you can buy. So there's a aquitard, aquifer, aquitard, aquifer, right? So there's both of the Floridan aquifers, the upper and lower, are both confined for most intents and purposes. But even that changes depending on where you are. We'll talk about that too. So this whole system was deposited on the continental margin of North America. Sea levels were variable, but at max, they're about 300 to 350 feet higher than they are today, which means a lot of Florida and the sort of Piedmont coastal areas of South Carolina, Georgia, Alabama, all of these were sort of a shallow tropical sea. North America was actually closer to the equator at this time too, so it was very warm. That's why we have so much limestone. Limestone is deposited in tropical oceans. So think of the Bahamas. There's active limestone deposition in the Bahamas. There's active limestone deposition down in Florida Bay, right? So these are sort of warmer regions where we produce limestone. So all of this would have been under the ocean, right? And this is, we're talking, everywhere between 150,000 years ago to as much as 3 or 4 million years ago. Okay, so just to talk about karst a little bit more, all of these limestones would have started out solid, right, as solid rock. But here's the trick. We infiltrate rainfall through these limestone bodies. And rainfall in general has an acidity of about 5, so there's a pH of about 5. If you remember your pH scales from chemistry, 7 being sort of neutral pH, so most of our body, right, so the fluids in our body are about a 7. Ocean water is actually slightly basic, so it's higher than 7, about 8.3. But most rainfall is actually around 5. It comes down quite acidic comparatively. So the more acid a rainfall is, in other words, the water is, the more potential it has to erode out or dissolve the limestone. So through time, as this sort of acidic rainfall flows through the limestone, it ends up dissolving it out, right? And we end up with something that looks like this. This is a cliff face. I think this one's actually from Kentucky. And what we're looking at are a series of just caves, right? Caves and cavities where this rock that used to be underground and used to be completely saturated with water is now lifted up and it's higher than the water table. But we can see the effects, right? So we can see the amount of dissolution that happened in this rock body. And this is what makes this rock so porous and so permeable, right? Is these suddenly the appearances of caves and cavities. All right, so if we sort of walk through what our different systems have and what they're made out of. As we go from left to right, we're going from sort of a competent bedrock or a clay, so something more solid, to something unconsolidated like sediment or sand. Fractured rocks, that's put in there for fracking. If we break up solid rock, that's what it looks like. And on the far right, we have karst, right? So a karst aquifer with these sort of conduits and holes. So on the far left, that confining layer, the Hawthorne Formation, really is made up of clays. So these sort of limey clays, lenses of sand, more or less sort of big river input, stuff we'd sort of be seeing coming out of the Mississippi today, right? So we're not talking about, solid rock or like plastic or something. It really is still porous, so it has water in it. And you can still pour water through it, so it does have a level of permeability, but it's really low compared to everything around it. So what it does is it sort of starts to act like a slowdown or a stop for water flow. So that's what we call it, an aquitard or a confining layer. The superficial aquifer system is made up of unconsolidated sediments for the most part, so these sands. So highly porous, much more permeable, makes great aquifer material. It's easy to pump. So that's what's sitting above the Hawthorne group. So the second one's what's sitting above it. What's sitting below it is the stuff on the far right, right? That's the Floridan aquifer and the karst. So this is kind of like a sandwich in some ways. You've got the Floridan aquifer below. You've got this competent sort of clay layer in between that acts to separate them. And then you have the unconsolidated sand sort of sitting on the top. Now, when we think about this, and I'm going to show you some images in a minute of sort of cross sections through the Floridan system, it is not uniform, right? So the presence of the Hawthorne Formation in the cross section is variable. It's thicker in some places, it's thinner in other places, and there are numerous places where there are holes through that aquitard. In other words, there are conduits that water can pass in between the superficial aquifer and into the through the Hawthorne Formation into the Floridan aquifer. So there are places these things are connected. And another thing to keep in mind is anytime you drill a well through the unconsolidated sediments and through the Hawthorne group into the Floridan, you are creating a new conduit in between those two aquifer systems. So if anything would happen to the competency of the well, a well creating fractures, things like that, and it has happened in the past, you are now more or less making a direct linkage between the two aquifer systems. So you need to be thinking about that when we think about contamination, things like that. All right, so here's our sandwich, right? So here's just one sort of cartoony depiction of what this looks like. Here's our Floridan aquifer near the coast. So the left-hand side would be the Piedmont. The fall line is sort of that break between what used to be the coastal plain in the past and what the sort of land was in the past. Now our sea levels are lower, so the Atlantic is further away from that fall line. But what you can sort of see here in the layering, so up on top, that sort of yellowish layer, that's the superficial aquifer system, right? So it's thicker near the coast, it's a little thinner as you go in, but it's pretty extensive, and it sits on top of most of all of the Southeast. There's some exceptions we'll talk about. I'll show you in a map in a moment. So that superficial system is thin, and that's made up of these unconsolidated sediments. The Hawthorne group, you can sort of see that upper confining unit, the next layer down, so that sort of peachy color. The Hawthorne group is that set of clays and sands that are much more less permeable than the stuff above it. So in some places, the Hawthorne group or parts of it would actually be considered an aquifer because you can pump water out of them. But here they're considered an aquitard because the formation above and the formation below are so much more permeable. All right, so as you drop below the Hawthorne group, this big section lower than that, this is the upper Floridan aquifer. right? So as we go down in the upper Floridan, we hit this layer here called the middle confining unit. It's a variable layer of karstic sort of cementing. So if you can think about this as a process, the surface of limestone can actually get armored after it rains on it enough, and can create a semi-confining unit. So it sort of breaks the difference between our upper Floridan and our lower Floridan aquifer. So the upper Floridan is here. We have this middle confining unit, then the lower Floridan aquifer. Then when we get down, we get into these other aquifer systems that are sort of much, much deeper. They're broken up by these clay layers, some more clay layers. And as you get further and further down, this water is much more mineralized, is not quite as good for drinking water. You can use it, but now we're talking about drilling down 1,000 meters and 2,000 meters. So they become very, very deep wells that are actually quite expensive to maintain. So that's why we sort of stick to this upper level of the Floridan aquifer. Now you'll also notice a couple of interesting things also happening. Fresh water actually flows out of the Floridan aquifer into the Atlantic Ocean, right? So water will flow through this system and deposit or discharge into the Floridan, from the Floridan into the Straits of Florida or off of our coastline. You notice as you get down here, this sort of layer between our salt water and our fresh water, there's saltwater intrusion into these aquifer systems as you get closer to a coastline too. And there's some cities that have had problems with this, like Miami, like Jacksonville. If you go up to Brunswick, they've had issues with this of salinization of their wells. And that's going to be from overpumping, which is where we're sort of headed next. So I just sort of want to give you this idea of sort of how this system layers up. So everything we're talking about with this mine is going to be occurring in that upper part of the system, in the superficial aquifer system, but they're proposing to pull water from the upper Floridan, right? So they're going to be drilling a little bit deeper and pulling some water out of the upper Floridan aquifer. So sort of a different cartoony system, if this works better for you. If we start pumping these different systems, here's sort of what happens. If we have these wells on the right that go into these sort of parts of the superficial systems, you're going to be drawing from that water table at the surface, right? So we're drawing water from that layer at the very top. As you drill down and puncture into these lower aquifer systems, you start drilling down into confining layers, into the Floridan aquifer. So water is going to flow further up the well, right, and be a little easier to pump. So the Floridan aquifer is much, much larger than the superficial aquifer system. So you can pull a lot of water out of the Floridan aquifer, and we'll talk about what pumping out of the two different systems does. All right, so sort of going from somewhat north to south. So if you think about the left-hand side being up dip or towards Georgia and South Carolina, and the right-hand side sort of closer going down dip towards Florida. The system gets thicker as you go south. So you can sort of see it thickening as you go from Georgia down to the Miami area. And you can sort of see what happens to these confining units, right? So if you get far enough up dip on the left-hand side, the Floridan aquifer is exposed at the surface, right? So there are parts of sort of central Georgia and Florida, central Florida, that have the Floridan aquifer exposed at the surface, right? So that's its recharge areas. If you move off of that recharge area, here's this sort of unconsolidated superficial aquifer that runs as this thin layer on the top. And that green is our upper confining unit. So this is the Hawthorne Formation. Now you'll notice even within the Hawthorne Formation, we have these lenses of more limestone material, right, that can make aquifer systems. So municipalities can draw from those. So this upper confining unit, we like to think of it as this sort of clay layer that separates it entirely, but it's actually got other lenses in it. And you'll see even in some places, these breaches, they're breaches that go through this confining unit. And these breaches aren't that well known. In other words, we don't have a great way of predicting where they are or when they occur, unless you happen to drill through one. Right. So in some cases, that's one of the worries about anything when you start messing with the upper or superficial aquifer system is you don't know how connected it is to the lower or the Floridan aquifer system. And if you're using the Floridan aquifer for your drinking water, you want to try to keep that clean, right? So you don't want to put anything that may end up there. Because in a minute, we'll talk about how hard it is to actually clean up a confined aquifer. It's almost impossible. All right, so sort of even the more technical version, if you will, I just wanted to point this out because you can sort of see as you move north, the Hawthorne Formation gets quite thin compared to the south, right? So there's a lot of misconceptions about what the Hawthorne group is. It's highly variable. It's made up of clays, sands, and limes, or limey muds and limey sands, right? So in a lot of places, if you go out west, there are parts of the Hawthorne group that would be the preferred aquifer of choice, because the other stuff around it, say you had like lava or basalt sitting below it and you're in Washington. It's very easy to pull water out of something that's unconsolidated or sedimentary versus something that's basically solid lava, right? So there's a difference here because the stuff that sits below it is so permeable. It basically turns the Hawthorne group into a confining layer. But I just want you to keep that in mind. It's all relative, right? So the Hawthorne group acts like a confining layer here, but its thickness is variable and its composition is variable. All right, so sort of an overview of what the Floridan looks like. I have some other ones from this, but this one's is neat because it has some of the sort of bigger features. So places like on the east of Georgia here, this embayment, we have two sort of lows in, and what I want to say, lows in elevation, right? So there's a reason the St. Johns River flows out sort of at this boundary, and the St. Mary's River flows out at this boundary. They're following this low embankment here, right? So this is a trough, if you will, of water that will collect and flow out to the ocean. On the western side, this is the Apalachicola River, right? Follows down this other low. As you move through the arch of Florida, if you want to talk about highlands in Florida, right? This is the highest area of Florida that runs through Lake Ocala and Orlando. It's called the Peninsular Arch. It's where some of the highest elevations in that part of Florida are, which means it acts like sort of a divide of water, with water either flowing to the west or the east from Florida through that. So these are sort of the relevant ones around here, right? So when we're talking about the St. Mary's River and which direction it flows and the St. John's, they're going to flow up to that embankment, right? In other words, over the embankment and into the trough, and then out to the Atlantic Ocean. And I'll point out that it's not just rivers that do this, right? So groundwater will also follow these same sorts of contours, especially in our superficial aquifer system. So they're going to flow from the superficial aquifer up here. All these directions are all going to flow towards the St. Mary's. So the St. Mary's is a gaining river because the groundwater flows into the St. Mary's as it goes to the ocean. Now, the other colors on here, right? So with that dark green, this is where the Floridan aquifer is thoroughly confined, right? So the overlying unit is thick enough and competent enough that if you drill into the Floridan aquifer, it behaves like an artesian aquifer. The sort of light green is semi-confined or thinly confined, right? So this sort of marginal stuff in here, over here, which means there are a lot of holes in it. And this is sort of a generalized map, so realize there's a lot of variability in here as they do not drilled holes in all of these areas. And then finally, this sort of light sort of green, this very light color, this is where the Floridan aquifer is unconfined. In other words, it's where it crops out at the surface. So if we think about where this is, right, so this portion of Florida down here that runs through Ocala, this area is highly unconfined. Water can recharge into the aquifer system. And this is where all our springs are, our big first magnitude order springs. And that's that confinement up here actually flowing out and discharging to springs, which then feed rivers that flow into the ocean. Up north here in sort of southwest Georgia and the Panhandle, there are more springs that are up here in this area. So Salt Spring, Radium Spring is up here. So there's some bigger spring areas there. Springs are much less common to the eastern side and the eastern side of even this part of the peninsula. There still are springs, they're just more minor, right? So they're not as strongly flowing.
So you have about 4 minutes, Jeremy, before 1 o'clock.
Or Q&A? Okay.
Yes.
I'm just going to get through a couple other concepts because I want you to understand how this works. All right. So the last piece is, again, where are Floridans exposed and where the hawthorn group's exposed. So the hawthorn actually crops out at the surface too. So what happens if we start pumping this system? Spring, wetland, that's also served by our water sources. So that's the Okefenokee. It's groundwater fed. If you start pumping, so this is sort of the idea here. Here's our system natural on the top. Here's our system with a pumping system in it. So you'll notice that this high capacity pumping well, which is what they're going to have to put in to drain that pit, right? You'll notice that it changes the groundwater table in the superficial system, and it's going to change the flow paths, right? And this can start to pull water out of the aquifer, which is what it's supposed to do, right? But it could start lowering levels in water bodies around it. So when they're talking about that 5 millimeter drop from their modeling, well, it's the best modeling can say, but what that's saying is it's going to have an impact. In other words, it's going to start draining water. And what we really worry about is during times of drought, right? Are you going to drain water continuously and make that drought worse? Or are you going to extend times of dry times in the swamp or even the river? What are those effects going to be? And those are the questions I ask when I start seeing these kinds of projects. So examples, Keystone Lake in Central Florida, those lakes are gone, right? We pumped enough out of the Florida aquifer that their lakes are gone. There's some nice high and dry docks on the lower right. This is near Tampa. Sanford Lake was actually a large, extensive wetland that was fed also by the aquifer system. The aquifer is drawn down to a point where that wetland is essentially gone. It's been replaced by sort of a wet prairie and more or less a dry prairie at a number of times of year. Okay, so what's the worry? Here's my worry. There's the mine located on a ridge, right? If they start pulling water from these pits, I have two things I'm wondering about. A, what's the draw in the local water table going to be? Are you actually going to be drawing water out of the Okefenokee, out of the St. Mary's River into this system if you start drawing it down enough, especially when we start hitting drought conditions? Because the groundwater's still there, it's just deeper, and if it's still there and you're pumping it, that's going to be a problem for these local areas. So consequences, there are different things to think about. The drawing from the Florida aquifer is a little bit less, I think, of a worry than the drawing from the superficial aquifer. So pumping out that mine, that's what it's gonna do, right, to our river, the swamp. Well, how much are you gonna draw down the Florida aquifer from that area? When you draw in a confined system, you don't put a cone of depression like we saw the lines going towards that well. That doesn't really happen in a confined system. You just draw water from further away within the confined system. So we have lots of questions about unintended consequences, right? You can't model a very complex system with a whole lot of confidence. It requires testing, and it requires actually, figuring out what these things are going to do. Okay, I'm a professor. I profess too much and talk too much. So people ask questions, and I'll see what I can answer.
All right, so we do have a few in the Q&A, Jeremy, so I'm going to read them to you, and if you'd be happy to answer them. There were a couple that I were able to answer, which you eventually did answer also. So one person has asked, are the recharge areas in Florida mapped, and are they protected?
They are mapped. A lot of them are mapped. The protections, they are technically protected, but that's as much as you can make a law and make people enforce that law. So often the protections have exceptions. You're not supposed to dump or anything around these recharge areas. But even the recharge areas are not homogeneous, right? So there are areas that are mapped as recharge zones that are not protected. So if it happened to be identified on private land, the protections are much more suspect. Okay, the Swanee and St. Mary's rivers seem to coincide with the big trough that separated Florida from the mainland millions of years ago and caused the Appalachian erosion to the east, exactly, and allowed Florida to be populated by corals. Are these two rivers far too young for this? Yeah, the rivers are much younger. They're less than 6,000 years old. We're talking about the sedimentation in the Swanee Trough, things like that. Those things are going to affect flow, but that's in a very general way, right? So the rivers are following lows that existed in the sedimentation. The biggest questions are going to be around the kinds of sediments, so the Hawthorne group versus the limestone versus the sand, right? That's when we look back in time to figure out where these things were coming from and what the systems might look like that give us a better crack at sort of modeling them.
All right. Well, I know it's a little bit past 1, just so if you need to hop off, if your lunch is over, please feel free to log off. This will be recorded, or this is being recorded and will be on our website, so you can follow up with the rest of the questions. But if y'all are able to hang out for just a few more minutes, Dr. Stalker, are you for just a couple more? Okay, because I have additional questions, and if anybody else has any, but I want to be respectful of people's time. So just follow back up if you have to pop off the meeting, everybody. So a couple of things as you were talking about that I wanted to ask some questions, Dr. Stalker, is so one of the things that I've always mentioned is that the water levels of the swamp drastically impact the water levels of the St. Mary's River. But really, the St. Mary's River as a gaining system is impacted by the water table. So whenever you go kayaking on the St. Mary's River, which a couple of us have done several times, we're actually at the water table. So when we're reading 3 feet, that's the water table right there. And so It's not just the swamp water that's flowing to the St. Mary's River. It's all the water coming from the superficial aquifer through the ground.
Yep, so that ridge is feeding probably a significant amount of water to both the Okefenokee and the river itself. Yeah, so some of it's runoff. I want to say all of it's groundwater, so some of it's direct runoff from rainfall. But you notice the river's flowing, right? Even in times when it's not raining or hasn't rained for a long time, and there's water in the Okefenokee, that's water table water. So that's groundwater interacting with the surface.
Yeah, and one of the things that another professor has mentioned is he's like, it's never zero, it's never dry, right? It's just zero flow. So the upper St. Mary's, that's most impacted by the swamp. Once you get more of the tributaries, you'll get more flow from those other sources. But the upper St. Mary's can have zero flow because the swamp has really much zero flow.
Right.
And
so
the ground is
not
low.
flowing out. The groundwater is below the surface there, right? It's deep enough below the surface that even the Okefenokee is probably feeding the aquifer at that point. But all those tributaries that come off, right, all of those are going to be groundwater fed too.
Oh, very interesting. So there were a couple of other questions in the Q&A. Where can I find the recharge maps?
So the USGS has a great, I can actually send you a link if you want to the paper. They did a big study on the Floridan aquifer, and it has more maps than you ever want to look at, right? It has the recharge zones, it has the thicknesses, it has the water levels. So I can send that to you if you want to do a little bit more studying about where these things are spatially.
All right, and then someone has a plug, so I'm just going to keep going with my questions, and then we'll get to that one. So the soils that are going to be excavated up to about 50 feet, at different areas, is all going to be homogenized, which means right now they're just layered out, like you mentioned the cake reference or analogy. But once you dig it out, you're going to mix it all back up. So that's going to change how water moves through the soil down, potentially down towards the Hawthorne layer. So the mining company has proposed that to kind of slow the water down is to put a bentonite clay layer down, 10.9% bentonite clay layer, and it's approximately going to be 3 feet thick. Is that something you've heard about being used before?
Yeah, so
they're going to do it horizontally, not vertically.
Fairly typical of filling, say, landfills or mining, is they'll put a thick layer of clay on the bottom. It is successful to some degree at stopping the flow of water from that system into the lower system. But generally in places like garbage pits, they line the whole pit. They don't just line the bottom of it. They line the sides of it too. So it prevents flow even laterally out of the pit. So in this case, if they just lay it on the bottom, yeah, it's going to prevent it from going directly down. But as we saw from all of these cross sections, right, water just doesn't flow down, it flows sideways. So water would flow out of the pit through the walls, right, of the pit they dug and head towards the river, or head towards the swamp or wherever. So there could be a change in the hydrology, and whatever they use to process that sand, right, as clean as they want to make it and put it back in the pit, anything that's in that processed sand is now going to be flowing into the aquifer system unless you prevent it from doing that. So would the clay layer be effective? Yeah, it's pretty typical. And it will slow the water down. It won't stop it, but it'll slow it down. And maybe that would alleviate some of the water flow, but if they're not lining the entire thing, you're just going to be moving around it, right? So you create a wall with two ends that stop, the water's going to flow around the wall, right? So that's one of the problems with seawalls, right? Your house is saved, but the one next to it is not.
So another interesting point I heard that you mentioned was actually the well cracking, the possibility of wells cracking that are going into the Florida aquifer and how that may contaminate the superficial aquifer or also move the superficial aquifer into the Florida aquifer.
Yeah.
So I guess what is the biggest concern? What would make a well crack? Would it be time? I don't know how fast they're going to be drilling these holes.
So you'll contaminate during the drilling process because you have to keep the hole open with drilling muds. So you drill into the aquifer, you hopefully clean it out, but you're puncturing the hole then. Depending on what they use for casing. So PVC casings can crack from just earth movement, creep, things like that. So the earth is not totally still, not on a long-term basis, right? So it can crack those. Stainless steel wells do actually still corrode and can start to become porous. And that's a problem they have with much older wells that are drilled into the Floridan, is they've sort of lost their competency through time. And it started to leak. So we call them leaky wells, which means anything in the upper aquifer system mixed into the lower aquifer system or vice versa. One of the big problems we have, especially in the South around biosolid projects, right, are where we have holes that go to the Floridan aquifer. Once you get contamination in the Floridan, there's really no way to get it out. It's in there. And if you use it as a drinking source, you can start to do the math yourself. It's not going to be a happy time.
And the future of these two wells is unclear just because they're getting permitted just for this one site, but the company owns 8,000 total acres. So, and they've been very clear that they're going to mine for 11 years, which means that they're going to be moving northward. So we don't know if these two wells are going to be for the duration of the mine or just for this site. So how do you cap wells? Is there a monitoring? Like after a mining project is over, who's in charge of the upkeep of those wells so they don't leak and they don't break?
Right. So usually the mining company is in charge of that, right? So while they're in business, and that's something I'll take up in a second, while they're in business, they are responsible for capping and monitoring those wells. However, what happens to almost every business, chemical, mining group that I've known, they're going to be out of business in 20 years, right? So then who's in charge of those wells? It's us, right? We're in charge of monitoring those and keeping them up. So often what happens is the taxpayers begin the long-term cleanup on these areas that the mining company, took care of while they were using it. But when it starts to become too expensive and they're not making money off of their mining anymore, but they're still having to monitor the reclaimed areas, they declare bankruptcy and hand it over to the state and go build another mine somewhere. So this is a continuous problem we have, right? Is this sort of long-term effects that are not considered in these short-term permits.
They're not very sustainable.
They're not, yeah. Well, none of this is, but that's that's how it works.
Well, those were all of my questions. So Dr. Stalker, I'm going to ask you to stop sharing, and then I'm going to show my last slide just of showing people or letting people know what you can do today to be able to make an impact. So we do have a series of educational events. So we do have our Lunch and Learn next Thursday, March 16th, talking about ecotourism and gateway communities. The public comments coming up, again, it's March 20th at 4:30 p.m. to the Georgia EPD. This is not a federal issue. This is not a federal public comment, although the feds have made a comment on it from the Department of Interior in regards to the Okefenokee Swamp. The St. Mary's River would greatly appreciate it if you added them into your public comment, because even as you read the permit, if you so choose to take that on, it's a lot to take on. It'll say neighboring tributaries, neighboring water body. It's actually never even in the permit. It's all about the Okefenokee Swamp. So we're trying to draw attention to the St. Mary's River. Urge your elected officials to support a healthy St. Mary's River and watershed. The city of St. Mary's just passed a resolution supporting the healthy Okefenokee Swamp and the St. Mary's River. And then encourage your Congress members to urge the Department of Interior to list the Okefenokee National Wildlife Refuge as a UNESCO World Heritage Site. You can go on their website, okefenokeeworldheritage.org, and you can support their efforts. So that's a great way of protecting the Okefenokee. And I just want to say thank you, Dr. Stalker, for taking the time out of your day, your busy day, to talk to us and walk us through this. I always enjoy our conversations. I learn so much, and you teach it in such a great, understandable way that it really just helps clarify a lot of things. And you answered a lot of my questions as well. But if anybody else has any other questions, feel free to email me and at emily@stmarysriverkeeper.org, and I will share them with Dr. Stalker and get you an answer. And I'll have this recording up online in the next 24 hours. And I hope you can join us next week for our final episode of for our River webinar series. Thanks everybody so much, and enjoy the rest of your day.
Thanks, Emily.
Thanks, Dr. Stalker.